Determine all intervals of increasing trend or decreasing trend and determine the coordinates of all maxima, minima, plateaus, or cliffs for the function f of x equals x times the square root of 3x plus 27. The first thing to do is find the domain. F of x equals x, a polynomial term, the domain would be all reals, times the square root, an even root, of 3x plus 27. We can rewrite the square root as a fractional exponent. It will be 3x plus 27 to the first power, second root, 1/2 power. The denominator of a fractional exponent is the root. It's an even number here, and the domain of an even root is not necessarily all real numbers. The domain requires that what is inside of an even root has to stay greater than or equal to 0. So 3x plus 27 has to stay greater than or equal to 0. We can solve for x by subtracting 27 from both sides and dividing both sides by 3. The domain requires that x is greater than or equal to -9. So the domain will start at -9. It includes its square bracket. It has no upper bound, so it'll go to positive infinity. The next thing to do is find all critical numbers. We will take the first derivative. F of x is a product of two expressions here, so the first derivative will require the product rule. The derivative of the first is a 1 times the second left alone, 3x plus 27 to the 1/2 power, plus the first left alone, x, times the derivative of the second, which is a power rule, bring down the power. Leave the inside alone. Subtract 1 from the power, I will call that 2/2, and then multiply by the derivative of the inside, which is a 3. So f prime of x equals, the first term of the derivative is 1 times an expression. 1 times anything is that same thing, so it'll be 3x plus 27 to the 1/2 power. Plus, in the second term, we can put the constants together. Everything's multiplied here. 1/2 times 3 is 3/2. There is an x, and there is a 3x plus 27 to the 1 minus 2 negative 1/2 power. Since the second term has a negative power, we will need to rewrite it so that it has a positive power. So we have a 3x plus 27 to the 1/2 power, plus in the second term there's a 3 in the numerator. There's an x that will stay in the numerator since it is to the positive power. There's a 2 in the denominator due to the 3/2, and we can move the 3x plus 27 to the denominator to become positive 1/2 power. As soon as one or more terms in the first derivative have a denominator, we have to combine all terms together over a common denominator so that the first derivative equals a single fraction in order to find critical numbers. The first term here does not have a denominator, but we can multiply it by 2 times 3x plus 27 to the 1/2 power over itself, a form of 1, so that we do not change the value, just a look, to give it a common denominator to the second term, which is 3x over that same denominator. The first term, we can multiply this numerator out. There's a 2. I'll move it to the front. 3x plus 27 to the 1/2 times itself. Because of matching bases, we can add the exponents. 1/2 plus 1/2 is 2/2, or first power. So we have a 2 times a 3x plus 27 to the first power. And we can combine it with the numerator of the second term, which is a plus 3x, because the entire thing is now over a common denominator of 2 times 3x plus 27 to the 1/2 power. We can distribute the 2 in here in the numerator. That will give 6x plus 54 plus the 3x all over 2 times, and the 1/2 power can be rewritten as square root of the 3x plus 27. We can combine like terms together in the numerator. The 6x and the 3x combine to be 9x plus 54. Over 2 times the square root of 3x plus 27. We want to fully factor the first derivative, except for inside of an even root. In the numerator, there is a common factor of a 9. Factoring it out, we'll leave behind an x plus 6. In the denominator, there's a common factor inside of the square root, but the square root's an even root, and there's no need to factor it, so we'll leave it as 3x plus 27. We now have the first derivative as a single fraction. All powers are positive, so we can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. Starting with the numerator, 9 times x plus 6 equals 0. We can divide both sides by 9. X plus 6 equals 0. Subtract 6 from both sides, and x equals negative 6. Now working with the denominator, 2 times the square root of 3x plus 27 equals 0. We can divide both sides by 2. Square root of 3x plus 27 equals 0. We can square both sides. Square root square cancel each other out, so 3x plus 27 equals 0 squared, which is a 0. We can subtract 27 from both sides, so 3x equals negative 27, and divide both sides by 3, so x equals negative 9. We will now check and see which of these are in the domain. The domain starts at negative 9 and includes negative 9, and everything greater up to positive infinity. X equals negative 6 is greater than negative 9. It's in the domain. We keep it. X equals negative 9 is in the domain by being the left endpoint of the domain. Both of these are critical numbers. We keep them both. We now are going to draw a domain line, a line representing the domain. It starts at negative 9 and it includes it. However, negative 9 is a critical number, and we are going to be taking the critical numbers out of the domain line. So by taking the negative 9 out, it will become not included, since it's a critical number. We also have a critical number of negative 6, which can be put on here. This breaks the domain up into 2 separate intervals. We can pick a test value inside of each of these intervals. Between negative 9 and negative 6, we can pick negative 8. And negative 6 to positive infinity, we can pick 0. We can now test the trend by plugging the test values into the first derivative. We do not care about the value of the first derivative, just whether it is positive or negative. So the best place to plug in will be the fully factored version. A couple of things about this. The denominator is a positive 2, that's positive, times the square root of 3x plus 27, which the domain has required that to already stay greater than or equal to 0. And the square root of something that is positive, times the positive 2 is still positive. That entire denominator is guaranteed to be a positive number. The positive 9 in the numerator is also positive, and that means that the only thing that matters here is the x plus 6. So we can plug the test values in the x plus 6. Plugging in negative 8 plus 6, that will be a negative number. A negative first derivative corresponds with a decreasing trend. Plugging in the 0 to the x plus 6. 0 plus 6 is a positive. We have a positive first derivative that corresponds to an increasing trend. So we have a decreasing interval from negative 9 to negative 6, and an increasing interval from negative 6 to positive infinity. We have 2 critical numbers here, negative 9. Negative 9 is a left endpoint. There is no function to the left of it, but to the right of it, it is decreasing. And that makes -9 be a relative maximum. It has an x-coordinate of -9. It'll have some y-coordinate that can be found by plugging the -9 in for x in the original function. So y equals f of -9, which is -9 times the square root of 3 times -9 plus 27, which is -9 times the square root of -27 plus 27, which is -9 times the square root of 0. And the square root of 0 is a 0, so the whole thing is 0. So this has a y-coordinate of 0. Right at the critical number of -6, we have the trend changing from decreasing to increasing. That makes -6 a relative minimum. So we have a relative minimum at the x-coordinate of -6. It will have a corresponding y-coordinate that can be found by plugging the x-coordinate into the original function, f of -6, which will be -6 times the square root of 3 times -6 plus 27, which is -6 times the square root of -18 plus 27, which is -6 times the square root of -18 plus 27 is 9. The square root of 9 is 3. -6 times 3 is a -18. And that'll be the y-coordinate of the relative min. So we have a decreasing interval, an increasing interval, a relative max, and a relative min.